The neutron has no electric charge. Zero. Nothing. It is one of the most electrically neutral objects in all of physics. And yet, if you place a neutron inside a magnetic field, something impossible seems to happen. It responds. It aligns. It precesses like a tiny compass needle, behaving exactly as if it were a miniature magnet. But magnets are made by moving electric charges. That is how magnetism works. No charge, no magnetism. That is the rule. So how does a particle with absolutely zero net charge generate a magnetic field? This is not a measurement error or a subtle artifact. The neutron's magnetism is real, precise, and has been confirmed by decades of experiments. It is used in hospitals, reactors, and laboratories every single day. Something with no charge acting like a magnet. That contradiction leads us deep inside the neutron, into a world where nothing is as empty as it appears. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something that seems simple, but turns out to be surprisingly deep. What is magnetism? Where does it actually come from? You have probably interacted with magnets thousands of times in your life. You stuck them on the refrigerator as a kid. You felt that strange, invisible pull when two magnets snapped together in your hands, and that equally strange resistance when you flipped one around and they refused to touch. Magnetism seems almost magical, an invisible force acting across empty space with no visible connection between the objects. But magnetism is not magic. It has a very specific and well understood origin. And that origin is electric charge in motion. In 1820, a Danish physicist named Hans Christian Oersted made a discovery that would change the course of science. He was giving a lecture demonstration and had a compass sitting on a table near a wire connected to a battery. When he switched the current on, the compass needle moved. It swung away from magnetic north and pointed toward the wire instead. This was completely unexpected. At the time, electricity and magnetism were considered entirely separate branches of physics. Electricity was about sparks and lightning and the strange tingling force you felt when you rubbed amber with fur. Magnetism was about lodestones and compass needles and iron filings arranging themselves in mysterious curved patterns on a sheet of paper. Nobody thought the two had anything to do with each other. They were taught as different subjects. They were studied by different people. They appeared in different chapters of different textbooks. But Oersted's compass needle said otherwise. A flowing electric current, which is simply electric charges moving through a wire, was creating a magnetic field around that wire. Moving charge was producing magnetism. This one observation, a compass needle twitching on a table in Copenhagen, cracked open one of the most important doors in the history of physics. Within a decade, the implications exploded outward. Michael Faraday in England demonstrated that the relationship worked in both directions. Not only did moving charges create magnetic fields, but a changing magnetic field could push charges through a wire, generating electric current. This was electromagnetic induction, and it became the foundation of electric generators, transformers, and eventually the entire modern electrical grid. Electricity made magnetism. Magnetism made electricity. The two forces were not separate at all. They were two expressions of one underlying phenomenon, intertwined at the deepest level. Then, in 1865, the Scottish physicist James Clerk Maxwell did something extraordinary. He took everything known about electricity and magnetism and wove it into 4 elegant mathematical equations that unified both forces into a single framework called electromagnetism. Maxwell's equations are among the most thoroughly tested and precisely confirmed equations in all of science. They describe everything from radio waves to visible light to the behavior of charged particles in magnetic fields. They predicted the existence of electromagnetic waves years before anyone detected them. And embedded deep in those equations, at the very foundation of the entire framework, is one essential principle. Magnetism arises from electric charges that are moving, spinning, accelerating, or otherwise doing something. Static charges sitting perfectly still create electric fields, but no magnetic fields. The moment those charges start moving, magnetism appears. This is not just an abstract theoretical statement. It describes every single magnet you have ever encountered in your life. When you hold a bar magnet in your hand, that magnet works because of the electrons inside its atoms. Electrons carry negative electric charge, and they possess a quantum property called spin. Spin is something we will explore more carefully later, but for now, the key point is that a charged particle with spin behaves like a tiny magnet. Each individual electron generates its own minuscule magnetic field, like a microscopic compass needle. In most materials, these electron spins point in random directions. Some point up, some point down, some point left, some point right. Their little magnetic fields cancel each other out, and the material as a whole shows no magnetism. But in certain special materials like iron, cobalt, and nickel, large groups of electron spins can spontaneously align in the same direction. When millions upon millions of electrons have their spins pointing the same way, their individual magnetic fields add together. They reinforce each other, and the material becomes a permanent magnet. The refrigerator magnet, the compass needle, the magnetic strip on your credit card, the enormous superconducting magnets inside hospital MRI machines. Every single one of them works because charged particles are doing something that generates a magnetic field. There are no exceptions to this. Magnetism requires electric charge, always, in every case, without exception. If something has no electric charge, it should have no magnetic properties whatsoever. If you could take an object and somehow strip every trace of charge from it, that object would be magnetically invisible. Place it in the strongest magnetic field ever generated, and it would sit there and do absolutely nothing. No response, no deflection, no torque, no precession. Nothing. Take away the charge, and you take away the magnetism. That is the rule. That is what 2 centuries of experimental physics established between any reasonable doubt. And this is exactly why the neutron created such a deep and genuine puzzle. The neutron was the last of the 3 basic atomic building blocks to be discovered, and it was the hardest to find. The electron came first, identified by J.J. Thomson in 1897. Thomson was working with cathode ray tubes, glass devices that shot mysterious beams through near-vacuum interiors. By deflecting these beams with electric and magnetic fields, and carefully measuring how much they bent, Thomson showed the beams were made of tiny, negatively charged particles with a mass far smaller than any atom. These were electrons, the first subatomic particles ever identified. Their discovery proved that atoms were not indivisible, as their Greek name suggested. Atoms had parts. They could be broken open, and inside was something smaller. The proton came next. Ernest Rutherford and his team performed the famous gold foil experiment in 1911, firing fast-moving alpha particles at extremely thin sheets of gold foil. Alpha particles are relatively heavy and positively charged, and the expectation was that they would pass through the foil with only minor deflections. Most of them did exactly that. But every once in a while, an alpha particle bounced back at a wild angle, and on rare occasions, one came almost straight back toward the source. Rutherford later said this was the most incredible event of his life. He compared it to firing an artillery shell at tissue paper and having it bounce back and hit you. The only possible explanation was that the atom's positive charge and nearly all of its mass were concentrated in a fantastically tiny, dense core at the center. This was the nucleus. The atom, it turned out, was almost entirely empty space. A dense, positively charged nucleus sat at the middle, and a cloud of electrons buzzed around it at an enormous relative distance. If an atom were expanded to the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. Everything else would be empty air. But the nucleus immediately presented a problem. Hydrogen, the simplest element, had a nucleus with 1 unit of positive charge and a mass of roughly 1 atomic mass unit. That made sense. 1 proton, 1 charge, 1 mass unit. Simple. Helium, the next element, had 2 positive charges in its nucleus, 2 protons. But helium's nuclear mass was not 2 atomic mass units. It was 4, twice what 2 protons alone would account for. Something else was hiding in there, contributing mass without contributing any charge. Rutherford recognized this discrepancy, and by 1920, during his Bakerian lecture at the Royal Society, he proposed that there might be a neutral particle inside the nucleus. A particle with roughly the proton's mass, but with absolutely 0 electric charge. He called it the neutron. But finding this invisible particle was a nightmare. Every detection tool in a physicist's arsenal relied on electromagnetic interactions. You spot particles by watching them ionize atoms, deflect in electric fields, bend in magnetic fields, leave visible tracks in cloud chambers. A particle with no charge does none of these things. It passes through matter like a ghost, leaving almost no detectable trace. For 12 years, the neutron hid in plain sight. Then, in 1932, James Chadwick at the Cavendish Laboratory in Cambridge cracked the problem. He bombarded beryllium targets with alpha particles and studied the penetrating radiation that emerged. Other researchers had performed similar experiments and assumed this radiation consisted of high-energy gamma rays, which are photons with no mass and no charge. But Chadwick performed meticulous energy and momentum calculations and showed the radiation could not possibly be gamma rays. It was far too penetrating. It knocked protons out of paraffin wax targets with far too much energy and momentum to be explained by massless photons. The only consistent explanation was that the radiation consisted of massive, uncharged particles. Particles with roughly the same mass as protons, but carrying 0 electric charge. These were neutrons. Chadwick had found Rutherford's ghost, and the discovery earned him the Nobel Prize in Physics in 1935. The picture of the atom was now complete. Every atom in your body, every atom in the earth beneath your feet, every atom in the most distant star is built from exactly 3 ingredients: protons, carrying positive charge, electrons, carrying negative charge, and neutrons, carrying no charge at all. Inside the nucleus, protons and neutrons sit side by side, bound together by the strong nuclear force. The neutron adds mass and helps stabilize the nucleus, but electromagnetically, it was assumed to be entirely inert. No charge meant no electromagnetic interaction of any kind, no magnetic moment, no response to electric or magnetic fields. The neutron was supposed to be the silent partner in the atomic nucleus, present but electromagnetically invisible. Now remember the rule we established. Magnetism comes from electric charge in motion. The neutron carries no electric charge. Therefore, the neutron should have absolutely no magnetic properties. This was not a guess or a rough approximation. It was a rigorous, mathematically precise consequence of the most fundamental equations in physics. Paul Dirac, one of the towering intellectual figures of the 20th century, had developed a relativistic quantum equation in 1928 that described how particles with spin 1/2 behave. His equation made specific, exact predictions about magnetic moments. For the proton, which is a spin 1/2 particle carrying 1 unit of positive charge, Dirac's equation predicted a magnetic moment of exactly 1 nuclear magneton. A nuclear magneton is a natural unit for measuring nuclear-scale magnetism, defined by the proton's charge, its mass, and Planck's constant. For the neutron, a spin 1/2 particle carrying 0 charge, Dirac's prediction was simpler still. 0. Not approximately 0, not very close to 0, not detectable only with extremely sensitive equipment, exactly, mathematically, precisely 0. The magnetic moment of a fundamental neutral particle, according to the deepest equation in quantum electrodynamics, is nothing. There is nothing to generate magnetism from, because there is no charge to move. So, in the early 1930s, physicists had every reason to expect the neutron to be magnetically blank. Drop it into the most powerful magnetic field you can create, and it should drift through without the faintest response. No twisting, no turning, no alignment. The magnet has nothing to grab onto, because the neutron has nothing electromagnetic to offer. That expectation was about to be destroyed. Otto Stern was a German experimental physicist with an extraordinary talent for precision measurement. He had already made history. In 1922, working with Walter Gerlach, he performed the famous Stern-Gerlach experiment. They shot a beam of silver atoms through a specially shaped magnetic field and watched the beam split into 2 distinct lines on a detector screen. This proved that angular momentum is quantized, that particles can only take on certain discrete orientations in a magnetic field, rather than pointing in any arbitrary direction. It was one of the landmark experiments of quantum mechanics, and it demonstrated that Stern knew how to extract profound physics from carefully designed beam experiments. In the early 1930s, Stern turned his precision techniques toward measuring the magnetic moments of atomic nuclei. In 1933, working with Otto Frisch and Emanuel Esterman, Stern measured the magnetic moment of the proton. The result was a shock. Dirac's equation predicted the proton should have a magnetic moment of exactly 1 nuclear magneton. Stern's measurement gave a value close to 2.8 nuclear magnetons, nearly 3 times larger than theory predicted. The proton was almost 3 times more magnetic than it had any right to be. This discrepancy was a serious red flag. It meant the proton was not a simple, structureless point particle. If it were, Dirac's equation would have nailed the prediction exactly. The fact that the measured value was so much larger meant something complicated was happening inside the proton. There was hidden structure, hidden motion, hidden electromagnetic activity. Nobody knew what it was yet, but the anomalous magnetic moment was a fingerprint of internal complexity. Still, the proton's magnetism, even if the exact number was wrong, at least made qualitative sense. The proton has charge. Charged things can be magnetic. The magnitude was unexpected, but the existence of the magnetism was perfectly reasonable. The neutron was a different story entirely. Stern's group also measured the magnetic moment of the deuteron, the nucleus of heavy hydrogen, which contains 1 proton and 1 neutron bound together. If the neutron had 0 magnetism, as Dirac predicted, then the deuteron's magnetic moment should simply be the proton's magnetic moment, adjusted slightly for how the 2 spins combine inside the nucleus. But the measured deuteron magnetic moment did not match this prediction. It was different from the proton value in a way that could only be explained if the neutron itself carried its own separate, non-zero magnetic moment. The neutron was contributing magnetism to the system. Not a tiny, borderline detectable contribution, a substantial one. By 1940, Luis Alvarez and Felix Bloch at the University of California devised an experiment to measure the neutron's magnetic moment directly, using a beam of free neutrons rather than neutrons locked inside a nucleus. Their approach was elegant. They passed a beam of neutrons through a carefully controlled arrangement of magnetic fields and measured the Larmor precession, the rate at which the neutrons wobbled like tiny spinning tops in the field. If a particle has a magnetic moment, it will precess in a magnetic field at a specific frequency that depends on the strength of the moment. By measuring this precession frequency with great precision, Alvarez and Bloch could extract the neutron's magnetic moment directly. The experiment itself was a masterpiece of ingenuity, and the details matter because they reveal just how hard it is to study a particle that refuses to interact electromagnetically. The first challenge was getting free neutrons in the first place. Inside an atomic nucleus, neutrons are stable. They sit there indefinitely, bound by the strong nuclear force, contributing mass and helping to hold the nucleus together. But a free neutron, a neutron outside a nucleus, drifting alone through space, is unstable. It decays. A free neutron has a half-life of roughly 10 minutes. After that, it transforms into a proton, an electron, and an antineutrino through a process called beta decay. This means you cannot stockpile neutrons in a jar and study them at your leisure. You have to produce them, form them into a beam, run your experiment, and collect your data before they disintegrate. Everything has to happen quickly, precisely, and on the first try, because the neutrons are literally vanishing as you work with them. Alvarez and Bloch obtained their neutrons from a cyclotron, an early type of particle accelerator. The cyclotron produced nuclear reactions that released neutrons, which were then collimated into a narrow beam and directed through the experimental apparatus. The beam itself was invisible. You could not see it, hear it, or feel it. Neutrons carry no charge, so they do not ionize the air they pass through. They do not glow, they do not spark, they do not leave trails. The only way to know the beam was there was to put a detector at the end and count the neutrons arriving. Working with a neutron beam is like working with a ghost. You know it exists because of the effects it produces, but you can never see it directly. The core of the experiment used carefully arranged magnetic fields to exploit the Larmor precession effect. When any particle with a magnetic moment is placed in a magnetic field, its spin axis does not simply snap into alignment with the field. Instead, the spin axis traces out a cone around the field direction, wobbling steadily like a gyroscope that has been nudged off vertical. This wobbling is called precession, and its frequency depends on exactly two things: the strength of the external magnetic field, which the experimenters controlled, and the strength of the particle's own magnetic moment, which was the unknown they wanted to measure. By tuning the experimental conditions and observing how the neutrons responded, Alvarez and Bloch could extract the precession frequency and from it calculate the magnetic moment with remarkable precision. But there was a subtlety that made this even harder than it sounds. Because neutrons do not carry charge, you cannot steer them with electric or magnetic fields the way you steer electrons or protons. You cannot bend a neutron beam with a magnet. You cannot focus it with an electric lens. Neutrons travel in straight lines, and the only way to select, sort, or filter them is through their nuclear interactions or through the very magnetic moment you are trying to measure. The experimenters had to design an apparatus where the magnetic effects on the neutrons were large enough to detect, but where every other source of noise, vibration, stray fields, temperature fluctuations, and statistical variation was suppressed to an extraordinary degree. The signal they were looking for was subtle. A slight change in how many neutrons arrived at the detector, depending on the precise configuration of the magnetic fields they had passed through. Extracting a clean measurement from this faint signal required both exceptional experimental skill and deep physical intuition. And the fact that the experiment worked at all, that it produced a clear, unambiguous result, tells you something important. The neutron's magnetic moment is not tiny. It is not some marginal, barely detectable quantity hovering at the edge of experimental sensitivity. It is large. Large enough that 1940s technology, decades before modern electronics or computer-controlled instruments, could measure it cleanly. A particle that should have had zero magnetism was broadcasting a magnetic signal strong enough to detect with equipment built during wartime. Whatever was happening inside the neutron, it was not subtle. The result was devastating for anyone hoping the neutron was magnetically simple. The neutron's magnetic moment turned out to be approximately -1.913 nuclear magnetons. Think about what this number means. A particle that Dirac's equation predicted should have exactly zero magnetism turned out to have a magnetic moment with a magnitude of nearly 2 nuclear magnetons. That is not a small deviation from zero. That is not a tiny correction that could be swept under the rug by some minor theoretical adjustment. The neutron's magnetic moment is enormous compared to what was expected. Its magnitude is roughly 2/3 of the proton's magnetic moment, and the negative sign carried its own message. While the proton's magnetic moment points in the same direction as its spin, the neutron's points in the opposite direction. Whatever was generating the neutron's magnetism, it was doing it in a way that reversed the expected relationship between spin and magnetic orientation. This result was deeply unsettling. Repeated measurements by independent groups using different experimental techniques confirmed it over and over. The number held firm. It was not a fluke, not a calibration error, not an artifact of some contamination in the beam. The neutron's magnetic moment is today one of the most precisely measured quantities in all of nuclear physics, known to better than 8 significant digits. There is absolutely no experimental doubt. The neutron, a particle with zero net electric charge, is a magnet, a genuine, measurable, precisely quantified magnet. So physicists were faced with a stark choice. Either their understanding of electromagnetism was fundamentally wrong, which seemed almost impossible given how spectacularly well Maxwell's equations and Dirac's equation worked for everything else in the known universe. Or the neutron was not what it appeared to be on the surface. And this second possibility pointed towards something profound. When most people hear that the neutron is electrically neutral, they picture it as a smooth, featureless, blank object, like a perfectly uniform grey ball. No charge anywhere on it, no charge anywhere inside it. Just mass, occupying space with absolutely no electrical character. But that is not what neutral has to mean. There is another way for something to be neutral, and this distinction turns out to be absolutely critical for understanding where the neutron's magnetism comes from. Imagine you have a ball with a positive charge concentrated on one side and an equal negative charge on the other side. If you measure the total charge of this ball from the outside, you get 0. Positive and negative cancel. The ball is neutral. But is there charge inside? Absolutely. There is a positive region and a negative region. Real charges. Real electromagnetic fields. The charges simply happen to add up to 0 when you total them. The ball's neutrality is not the result of having no charge. It is the result of having equal and opposite charges that cancel. Consider an even more familiar example. Think about an ordinary water molecule. A water molecule is electrically neutral overall. Its total charge is 0. But nobody would claim a water molecule has no electromagnetic character. The oxygen atom pulls electron density toward itself, becoming slightly negative. The hydrogen atoms lose some electron density, becoming slightly positive. The molecule has a positive end and a negative end. This separation of charge is called a dipole, and it gives water most of its remarkable properties. Water dissolves salt, conducts electricity in solution, and forms hydrogen bonds, precisely because of this internal charge separation. Neutral on the outside, deeply charged on the inside. You encounter this same principle in dozens of everyday situations without even thinking about it. Consider a standard 9-volt battery. Its overall charge is neutral. There is no net charge on a battery sitting on a shelf, but inside there are chemicals separated into regions of positive and negative charge, carefully arranged to produce a voltage. The neutrality of the battery does not mean it is electrically dead. It means the internal charges are balanced. Connect the terminals and current flows because the internal structure is anything but empty. Or consider the Earth itself. Our planet is electrically neutral overall. Its total positive charge from all the protons in every atom balances against its total negative charge from all the electrons. The net charge is 0. But the Earth has a magnetic field, a substantial one, strong enough to deflect compass needles and shield us from solar wind particles streaming out from the Sun at hundreds of kilometers per second. That magnetic field exists because of moving charges deep inside the planet. Currents of molten iron flowing in the outer core, generating magnetism through the same fundamental principle. The Earth is neutral but magnetic. Because neutrality only means the charges balance. It says nothing about whether those charges are moving. And moving charges produce magnetic fields regardless of whether the total adds to 0. Or think about an atom. Take a carbon atom. A carbon atom is electrically neutral. It has 6 protons in its nucleus with a total charge of +6, and 6 electrons surrounding the nucleus with a total charge of -6. The charges cancel. The atom is neutral. But inside, there is an enormous amount of electromagnetic activity. Electrons are interacting with the nucleus, occupying specific quantum orbitals, absorbing and emitting photons, forming chemical bonds with other atoms. The carbon atom's neutrality does not erase its rich electromagnetic interior, not even close. The neutron is similar in principle, though the details are radically different. Its neutrality does not mean it is electromagnetically empty. Its neutrality means that whatever charged things exist inside add up to 0 total charge. And here is the essential insight. Charged things that add up to 0 can still move. They can still spin. They can still carry angular momentum. They can still create magnetic fields. A collection of positive and negative charges, whose total is 0, but whose individual charges are in motion, will, in general, produce a non-zero magnetic field. The cancellation of charge does not automatically cancel the magnetism, because magnetism depends not just on how much charge there is, but on how that charge is distributed and what it is doing. This realization pointed to something revolutionary. The neutron must have internal structure. It could not be a fundamental, indivisible, structureless particle. If it were truly a single entity with no parts and no charge, its magnetic moment would be exactly zero, just as Dirac predicted. The fact that its magnetic moment is large and negative means there are charged things inside the neutron, arranged and moving in a specific way that produces magnetism, even while the total charge cancels to zero. The anomalous magnetic moments of both the proton and the neutron were among the earliest clues, the first whispered hints, that these particles were not elementary. They had insides, they had parts, and whatever those parts were, they carried electric charge and they were in motion. In the 1930s and 40s, nobody knew what those internal parts might be. The idea that protons and neutrons could be made of still smaller particles was not yet on anyone's radar. Physicists could measure the neutron's magnetic moment with superb precision, but they could not explain it. They could write down the number, they could confirm it in experiment after experiment, but they had no theory, no model, no mechanism to account for it. That answer would take 3 more decades to emerge. It would require entirely new physics, new particles, new forces, and a fundamentally new understanding of what matter is at its most basic level. The neutron's magnetic moment was a fingerprint left behind by something hidden, something deep inside. And reading that fingerprint would eventually lead to one of the most profound discoveries in the history of science. The discovery that protons and neutrons are not elementary particles at all, but are themselves built from smaller, more fundamental objects. The neutron's impossible magnetism was never a violation of physics. It was physics trying to tell us something. That zero does not mean empty. That neutral does not mean featureless. And that the deepest truths about nature are almost always hidden inside the things we think we already understand. For most of human history, the search for nature's smallest pieces followed a simple pattern. Take something, break it open, find smaller things inside. Molecules break into atoms. Atoms break into electrons and nuclei. Nuclei break into protons and neutrons. At each stage, the pieces seem fundamental, until someone finds a way to crack them open too. But after protons and neutrons were identified in the early 20th century, decades passed with no further progress. Nobody could break them apart. Nobody could see inside them. For a generation of physicists, protons and neutrons appeared to be the final answer, the rock bottom of material reality. And then, starting in the late 1940s and accelerating through the 1950s, nature threw a spectacular and bewildering curveball. Particle accelerators changed everything. These machines use powerful electric fields to accelerate subatomic particles to enormous speeds, and then smash them into targets or into each other. When particles collide at high enough energies, the energy of the impact converts into matter, creating new particles that did not exist before the collision. This is Einstein's famous mass-energy equivalence at work. Energy becomes mass. And what physicists discovered when they started running these collisions was utterly baffling. New particles appeared everywhere, dozens of them, then hundreds. Particles nobody had predicted and nobody had expected. They came in all sizes, all masses, all lifetimes. Some lived for billionths of a second before decaying. Others lasted trillionths of a second. Some had positive charge, some negative, some neutral. Some were heavier than protons, some were lighter. They had strange properties that demanded entirely new quantum numbers to describe. One group of these particles was so bizarre that physicists literally named the relevant quantum number strangeness. The particles had strangeness because physicists were baffled by their behavior. By the early 1960s, the zoo of known subatomic particles had grown to well over 100 species. Pions, kaons, eta mesons, rho mesons, lambda baryons, sigma baryons, Xi baryons, and many more, each with its own mass, charge, spin, and lifetime. It was chaos. Beautiful, productive, deeply confusing chaos. Physicists had spent decades organizing the periodic table of chemical elements into an elegant structure based on atomic number. Now they were staring at a new and far messier collection of objects with no organizing principle, no pattern, no obvious underlying logic. The situation was sometimes compared to stamp collecting. You could catalogue the particles, measure their properties, and sort them into groups. But without an underlying theory, you were just making lists. Where was the deeper structure? Where was the periodic table of subatomic physics? In 1961, a theoretical physicist named Murray Gell-Mann at the California Institute of Technology proposed something remarkable. Working independently, but around the same time as Israeli physicist Yuval Ne'eman, Gell-Mann discovered that the known particles could be organized into elegant geometric patterns based on their properties, specifically their charge and strangeness. He called his classification scheme the Eightfold Way, a poetic name borrowed from Buddhist philosophy. The Eightfold Way was not just a convenient filing system, it was predictive. When Gell-Mann arranged the known baryons, the heavier particles like protons and neutrons, into their pattern, he noticed a gap. One slot in the pattern was empty. No known particle had the right combination of charge, strangeness, and spin to fill it. So Gell-Mann did what great theorists do. He predicted that the missing particle must exist, and described exactly what its properties should be. He predicted its mass, its charge, its spin, its strangeness, and even the way it should decay. He called it the omega minus. In 1964, a team at Brookhaven National Laboratory found it. They sifted through tens of thousands of photographs of particle tracks in a bubble chamber and identified one event, one single cascade of particle decays that matched the omega minus exactly. The mass was right. The charge was right. The strangeness was right. The decay pattern was right. Everything matched Gell-Mann's prediction with impressive accuracy. This was a triumph. It meant the Eightfold Way was not just a convenient organizational tool. It reflected something real about the deep structure of matter. There was a hidden pattern beneath the chaos of the particle zoo. But what was actually producing these elegant geometric arrangements? Gell-Mann took the next step. In 1964, the same year the omega minus was discovered, he proposed that all the particles in the zoo were not fundamental at all. They were composites, built from a smaller set of truly fundamental building blocks. He called these building blocks quarks, a word he took from a passage in James Joyce's novel Finnegan's Wake. Around the same time, an American physicist named George Zweig independently proposed the same idea, though he called his particles aces. It was Gell-Mann's terminology that stuck. The proposal was audacious. Rather than hundreds of fundamental particles, there were only a handful of deeper building blocks, and all the complexity of the particle zoo arose from different combinations of those few ingredients. In their original proposal, quarks came in three varieties called flavors: up, down, and strange. We have since discovered three more flavors: charm, top, and bottom, for a total of 6. But for understanding the proton and neutron, only the up and down flavors matter. These are the lightest quarks, the most stable, and the ones that make up all the ordinary matter in the universe. Every atom in your body, every atom in the earth beneath your feet, every atom in the stars and planets is built from up quarks and down quarks, bound together inside protons and neutrons. Each quark flavor carries a specific set of properties, including, crucially, fractional electric charge. This was one of the most radical aspects of the quark hypothesis. Until quarks, Every known particle in the universe carried an electric charge that was a whole number multiple of the electron's charge. Electrons had -1, protons had +1, neutrons had 0. No one had ever observed a charge of 1/2 or 1/3 or 2/3. The electron's charge appeared to be the indivisible unit. Charges always came in whole numbers. Quarks shattered that assumption. In the quark model, the up quark carries an electric charge of +2/3, not +1, not +1/2, +2/3 of the electron's charge magnitude. The down quark carries a charge of -1/3. These are fractions, they are not whole numbers. Nobody had ever seen anything like this in nature before. At first, many physicists were deeply skeptical. Fractional charges? Particles that nobody had ever seen in isolation. Many people treated quarks as a mathematical trick, a useful bookkeeping device that helped organize the particle zoo but did not correspond to actual physical objects inside protons and neutrons. The quarks, skeptics argued, might be abstract mathematical constructs rather than real things you could, in principle, bounce other particles off of. The skeptics had a point. Nobody had ever detected a particle with fractional charge. Nobody had ever isolated a single quark and measured its properties directly. How could you claim something was real if you could not isolate it? But the mathematics worked, and it worked spectacularly well. The quark model explained all the known particles and their properties with stunning economy. Every known meson, the medium-weight particles, could be explained as a bound pair of one quark and one antiquark. Every known baryon, the heavier particles including the proton and neutron, could be explained as a bound triplet of 3 quarks. The masses, charges, spins, and decay patterns of the entire particle zoo followed naturally from different combinations of just 3 quark flavors. Hundreds of particles, all built from 3 ingredients. The simplicity was breathtaking. Now here is where this connects directly to the neutron's magnetism. In the quark model, a proton is made of 2 up quarks and 1 down quark. 2 particles with charge +2/3 and 1 with charge -1/3. Add them up. +2/3, +2/3, -1/3. That gives +4/3 -1/3, which equals +3/3, which equals +1. Exactly the proton's known charge. Perfect. A neutron is made of 1 up quark and 2 down quarks. 1 particle with charge +2/3 and 2 particles with charge -1/3 each. Add them up. +2/3, -1/3, -1/3. That gives +2/3 -2/3, which equals 0. The charges cancel. The neutron is neutral. But look at what just happened. The neutron's 0 charge is not the result of having no charged particles inside. It is the result of having 3 individually charged particles whose charges happen to sum to 0. There are real, genuine electric charges inside the neutron. Positive charge from the up quark and negative charge from the 2 down quarks. These charges are present, they are real, and they are substantial. They simply cancel when you add them together. Think of it this way. Imagine a building with 3 people inside. One person has $20,000 in savings. The other 2 each owe $10,000. The building's net financial position is 0, balanced perfectly. But that does not mean the building is financially empty. There are real assets and real debts inside. They just happen to cancel. And if those 3 people start moving around inside the building, conducting transactions, spending and earning, the building's financial activity could be enormous, even though its balance sheet reads 0. The same principle applies to the neutron. The total charge cancels, but the charged quarks are still there, still in motion, still carrying angular momentum, still generating electromagnetic fields. Cancellation of the sum does not eliminate the parts. But the crucial question remained unanswered through the middle of the 1960s. Were quarks actually real, or were they just a mathematical trick? This question was settled decisively by a series of experiments in the late 1960s at the Stanford Linear Accelerator Center in California. The experiments used a technique called deep inelastic scattering, and they were the quark equivalent of Rutherford's gold foil experiment half a century earlier. The principle was similar. You probe the interior of something by shooting small, fast particles at it and watching what happens. Rutherford had fired alpha particles at gold atoms and discovered the nucleus by observing how the alpha particles bounced. The Stanford experiments fired high-energy electrons at protons and neutrons and studied how the electrons scattered. If protons and neutrons were smooth, uniform blobs of matter with no internal structure, the electrons should scatter gently and predictably. They would bounce off a soft, deceive target. But if protons and neutrons contained small, hard, point-like objects inside, some electrons should scatter violently, bouncing back at large angles, just as Rutherford's alpha particles had done when they struck the dense nucleus lurking inside the atom. That is exactly what happened. Some electrons bounced back at wild angles with enormous energy transfers. The scattering pattern was unmistakable. It was the signature of small, hard, point-like objects inside the proton and neutron. The electrons were not bouncing off a smooth cloud. They were ricocheting off individual quarks. The experiments, led by physicists Jerome Friedman, Henry Kendall, and Richard Taylor, provided the first direct evidence that quarks were real physical objects, not mathematical abstractions. The three physicists shared the Nobel Prize in Physics in 1990 for this discovery. They had done for protons and neutrons what Rutherford had done for atoms. They had looked inside and found structure. Now, a natural question arises. If quarks carry electric charge, and quarks are real physical objects inside the neutron, what holds them together? Quarks have charges of +2/3 and -1/3. In principle, electromagnetic forces would act between them. But electromagnetism is far too weak to explain what actually happens inside the neutron. Something far more powerful is at work. The force that binds quarks together is called the strong force, and it is carried by particles called gluons. The name gluon comes from the word glue, because these particles literally glue quarks together. The strong force is the most powerful of the four fundamental forces of nature. At the distances relevant inside a proton or neutron, roughly 1 femtometer across, the strong force is approximately 100 times more powerful than electromagnetism. It completely overpowers the electromagnetic interactions between quarks and holds them in a tight, permanent embrace. But the strong force operates through a type of charge that has nothing to do with electricity. This charge is called color charge, and it comes in 3 varieties whimsically named red, green, and blue. These have absolutely nothing to do with actual colors. They are just labels, names given to 3 distinct types of strong force charge, analogous to how positive and negative label the 2 types of electric charge. Every quark carries one of these 3 color charges at any given moment, and just as electric charges must balance for electromagnetic neutrality, color charges must balance for strong force neutrality. A proton or neutron must be color neutral, containing 1 red, 1 green, and 1 blue quark. These three colors combine to produce a color-neutral object, similar in concept to how combining red, green, and blue light produces white light. Gluons are radically different from photons, the particles that carry the electromagnetic force. Photons are electrically neutral. They carry the force between charged particles, but they themselves carry no electric charge. This means photons do not interact with each other. Two beams of light can cross through each other without affecting each other at all. But gluons carry color charge themselves. They are charged under the very force they mediate. This self-interaction has extraordinary consequences. It means the strong force does not get weaker with distance the way electromagnetism does. Instead, it stays roughly constant, or even gets stronger as you try to pull quarks apart. Stretching the connection between two quarks is like stretching a rubber band. The farther you pull, the harder it pulls back. If you try to drag a quark out of a neutron, the strong force resists with ever-increasing strength. Eventually, the energy you pour into stretching the bond becomes so enormous that it converts into new quark-antiquark pairs, creating entirely new particles rather than releasing free quarks. This is why no one has ever seen a free quark in isolation. Quarks are permanently confined inside composite particles. You can never isolate one and hold it up to a camera. This phenomenon is called confinement, and it is one of the most remarkable features of the strong force in nature. This also means that the interior of the neutron is not a simple, static arrangement. It is not three little balls sitting at fixed positions like planets orbiting a star, or beads glued along a string. That mental picture, while tempting, is deeply misleading. The inside of the neutron is a seething, dynamic, quantum mechanical storm. The three quarks are not sitting still at assigned locations. They exist as overlapping quantum probability clouds, their positions and momenta governed by the Heisenberg uncertainty principle. You cannot point to a specific spot inside the neutron and say the up quark is right here. It does not work that way. The quark is smeared across a range of possible positions, and only the probability of finding it at any given location is well defined. And the gluon field binding them together is not a static scaffold or a rigid framework. Gluons are constantly being emitted and absorbed by the quarks. Virtual gluons flash into existence and disappear throughout the neutron's interior. Some of those gluons briefly convert into virtual quark-antiquark pairs that appear and vanish again almost instantly. The inside of the neutron is alive with quantum activity. A turbulent sea of quarks, antiquarks, and gluons, all interacting furiously, all confined within a space roughly 1 femtometer across. 1 quadrillionth of a meter, a distance so small that roughly 1 trillion neutrons lined up side by side would barely span the width of a single grain of sand. And yet, despite all this internal turbulence, the neutron's charge distribution is not random. It has structure. It has shape. And we know this because physicists measured it directly. Starting in the 1950s and continuing with increasing precision through subsequent decades, experimentalists performed electron scattering experiments aimed at mapping the internal charge distributions of both the proton and the neutron. The technique works on the same principle as sonar. You bounce a known probe off a target and study how the probe scatters to reconstruct what the target looks like inside. By analyzing how electrons scattered off neutrons at different energies and angles, physicists could extract what are called electromagnetic form factors. These are mathematical functions that encode how electric charge and magnetism are distributed spatially within the particle. They are essentially maps of the neutron's electromagnetic interior. For the proton, the results were straightforward, if somewhat surprising in their details. The proton's positive charge is concentrated toward its center and falls off gradually toward the edges. It is a fuzzy ball of positive charge, densest in the middle and thinning out at the periphery. A smooth distribution with no sharp boundaries. The neutron's charge distribution was far more interesting and far more revealing. Remember, the neutron's total charge is 0. If the charge were uniformly 0 everywhere, if the neutron were truly electromagnetically blank at every point inside it, the form factors would show nothing. A flat, featureless blank in the data. But that is not what the experiments found. Not at all. The neutron has a positive charge density near its center and a negative charge density toward its outer edges. The interior is slightly positive and the exterior is slightly negative. These two contributions cancel precisely when you integrate over the entire volume, giving a total charge of exactly 0. But they are not individually 0. There is real charge present at every point. Positive in the core, negative near the surface. A genuine internal electromagnetic landscape hidden beneath the veil of overall neutrality. The neutron's charge profile is not flat. It has hills and valleys. It has texture and structure that show up unmistakably in the scattering data. This is exactly what the quark model predicts. The up quark, with its positive charge of plus 2/3, tends to be found slightly closer to the center of the neutron on average. The two down quarks, with their negative charges of minus 1/3 each, tend to be found slightly farther out. This is not a rigid arrangement. Nobody is claiming the quarks sit at fixed addresses inside the neutron like occupants in assigned rooms. It is a statistical tendency, a probability distribution averaged over the quantum fluctuations of the quarks' positions and momenta. But the pattern is real, reproducible, and measurable. It shows up clearly and consistently in experiment after experiment. Think of it this way. Imagine a cloud that appears completely grey when viewed from far away. Uniform, featureless, perfectly neutral grey. You would never guess from a distance that anything interesting was happening inside. But if you could fly into that cloud and look around, you would find that the centre is actually slightly brighter, almost white, and the outer layers are slightly darker, almost charcoal. From outside, these differences average out, and you see only neutral grey. But inside, there is structure. There is variation. There is a bright core wrapped in a darker shell, invisible from the outside, but absolutely real from within. That is what the neutron looks like electromagnetically. Viewed from outside, it is neutral. Measure its total charge and you get 0. But inside there is a genuine charge distribution with real positive and negative regions, a complex electromagnetic interior that only reveals itself when you probe it with enough energy and precision. This interior charge structure is not a theoretical speculation or an inference from some abstract mathematical model. It has been directly measured by multiple independent experimental groups using different techniques over the course of decades. The data is clear, consistent, and beautifully explained by the quark model. The neutron's neutrality is real, but it is only a surface-level truth. It is the answer to one specific question: what is the total charge? And the answer to that question happens to be 0. But total charge is not the only question you can ask. You can ask how the charge is distributed. You can ask whether there are regions of positive and negative charge inside. You can ask whether those internal charges are in motion. And the answers to all of those questions are far more interesting than 0. Peel back the surface and you find a rich electromagnetic interior. 3 charged quarks, bound together by the furious exchange of gluons, arranged in a dynamic quantum configuration that cancels the total charge while preserving a complex internal charge landscape. 0 on the outside, deeply structured on the inside. And that internal structure is precisely what allows a particle with no net charge to behave like a magnet. The charges inside are real. They carry quantum spin. they exist in constant motion, and moving charges with angular momentum generate magnetic fields. The total charge cancels, but the total magnetism does not automatically cancel, because magnetism depends not just on the amount of charge, but on how the charge is arranged, and how it is moving, and how its spin is oriented. Two regions of equal and opposite charge, spinning and moving in different configurations, can produce a net magnetic moment, even though their charges sum to zero. That is exactly what happens inside the neutron. The cancellation of charge eliminates the neutron's electric identity, but it does not erase its magnetic identity. The quark's spins and internal motions conspire to produce a definite, measurable, non-zero magnetic moment from a particle whose total charge is nothing at all. Understanding how that conspiracy actually works, how quantum spin combines with the wild internal dynamics of a strongly bound three-quark system to generate the neutron's specific magnetic moment, requires us to go deeper still into one of the strangest properties in all of quantum mechanics. We now know what lives inside the neutron. Three quarks, one up and two down, bound together by gluons in a space roughly 1 femtometer across. We know these quarks carry real electric charges that cancel to zero overall, while maintaining a genuine internal charge distribution. But knowing the ingredients is not the same as understanding the mechanism. The question still stands. How, specifically, does the neutron's magnetism arise from these internal parts? To answer that, we need to confront one of the strangest and most misunderstood concepts in all of physics: quantum spin. Spin is the property that turns charged particles into tiny magnets. Without spin, there would be no magnetic moments, no compass needles, no MRI machines, no neutron magnetism to explain. Spin is absolutely central to this entire story. And it is also one of the most deeply counterintuitive ideas in quantum mechanics, which is saying something, because quantum mechanics is full of deeply counterintuitive ideas. The word spin naturally conjures a mental image. You hear spin and you picture something rotating. A top spinning on a table, a basketball twirling on a fingertip, the Earth rotating on its axis. These are all examples of angular momentum from classical physics, momentum associated with rotational motion. A spinning object has angular momentum because it has mass, and that mass is physically moving in a circular path. The faster it spins, or the more mass it has, or the farther the mass is from the rotation axis, the more angular momentum it carries. Classical angular momentum is intuitive. You can see it, feel it, measure it with a ruler and a stopwatch. So when physicists in the 1920s discovered that electrons seemed to possess their own intrinsic angular momentum, they instinctively called it spin. The electron was spinning, they assumed, like a tiny top. It had angular momentum because it was literally rotating about its own axis. Samuel Goudsmit and George Uhlenbeck, two Dutch graduate students, proposed this idea in 1925. They suggested each electron carried an internal angular momentum equivalent to spinning around its own axis, producing a small magnetic moment in the process. The idea worked beautifully to explain several puzzling experimental results, including the fine structure of atomic spectral lines and the anomalous behavior of electrons in magnetic fields. But almost immediately, serious problems appeared. If the electron were a little ball physically spinning on its axis, you could calculate how fast the surface would need to rotate to produce the observed angular momentum. The answer was absurd. The electron's surface would need to move faster than the speed of light, far faster. This is not allowed by Einstein's theory of special relativity. Nothing with mass can reach the speed of light, let alone exceed it. And yet the angular momentum was there. It was real, measurable, and had concrete physical consequences. It was not optional. It was not approximate. It was as fundamental to the electron as its mass or its charge. So physicists were forced to abandon the classical spinning ball picture entirely. Quantum spin is not rotation. It is not a particle physically turning around some axis. It is something else entirely, an intrinsic quantum property with no classical analogue. The electron has angular momentum, but it does not get that angular momentum from physically rotating. It simply has it. Spin is built into the particle at the most fundamental level, baked into the mathematics of quantum field theory, present from the moment the particle comes into existence. Trying to understand spin by imagining a spinning ball is like trying to understand electric charge by imagining a tiny bucket of fluid. The analogy captures some superficial features, but fundamentally misrepresents what is actually happening. Think about electric charge. An electron has charge, but that charge is not made of anything. It is not a substance sitting inside the electron. You cannot open up an electron and scoop out some charge. Charge is simply a property the electron possesses, a label that determines how it interacts with electric and magnetic fields. Spin is similar. It is a property, not a mechanism. The electron has spin 1/2, and that value determines how it behaves in magnetic fields, how it combines with other particles, and what statistical rules it follows. But there is no internal machinery producing the spin, no gears, no rotation, no spinning surface. Just a quantum number that the universe assigns to certain particles because the mathematics of relativistic quantum mechanics demands it. Now here is where spin connects to magnetism. In classical physics, if you take a charged object and make it spin around an axis, you get a magnetic moment. The moving charge traces out a circular current loop, and current loops produce magnetic fields. This is how electromagnets work. Run current through a coil of wire and you get a magnetic field. The faster the current flows or the larger the loop, the stronger the field. In quantum mechanics, spin plays an analogous role. Even though the particle is not literally rotating, its intrinsic spin still produces a magnetic moment if the particle carries electric charge. This is not an approximation or an accident. It follows rigorously from the Dirac equation, the relativistic quantum equation that describes spin 1/2 particles. A charged particle with spin automatically carries a magnetic moment. The spin and the charge together inevitably generate magnetism. This is a mathematical certainty, a direct and unavoidable consequence of the deepest equations we have. The size of this magnetic moment depends on two things: the amount of charge the particle carries and the mass of the particle. More charge means a stronger magnetic moment. More mass means a weaker one. For an electron, the charge is substantial and the mass is tiny, so the electron's magnetic moment is relatively large. For a quark, the charge is fractional and the mass is larger than the electron's, so each quark's individual magnetic moment is smaller. But the quarks are still charged particles with spin. Each one produces its own magnetic moment. Each one acts as its own tiny magnet inside the neutron. So now we can start to see the mechanism taking shape. The neutron contains 3 quarks. Each quark has spin 1/2. Each quark carries a fractional electric charge. Because each quark is a charged particle with spin, each quark has its own magnetic moment. The neutron's overall magnetic moment is the result of combining these 3 individual quark magnetic moments. But how do they combine? This is where things become subtle and fascinating. Each quark's spin can point in one of 2 directions relative to any axis you choose: spin up or spin down. These are the only options for a spin 1/2 particle. There is no spin sideways, no spin at 30 degrees, just up or down, and when measured along a chosen axis, it is always one or the other. The neutron itself has spin 1/2. This means that when you combine the 3 quark spins inside it, the result must total spin 1/2 for the composite particle. 3 spin 1/2 particles can combine in several different ways. The mathematics of angular momentum addition tells you exactly which combinations are allowed. Some combinations give a total spin of 3/2. Others give a total spin of 1/2. The neutron is a spin 1/2 particle, so we only care about the combinations that produce that specific total. It turns out there is a particular quantum arrangement of the 3 quark spins that describes the neutron. In this arrangement, 2 of the quarks have their spins pointing in opposite directions, partially cancelling each other, while the 3rd quark spin remains aligned with the overall neutron spin. The precise quantum state involves specific combinations of up and down spin orientations for each quark, weighted by mathematical coefficients that quantum mechanics dictates. The details are technical, but the essential point is that the 3 spins do not all point the same way. They are arranged so that partial cancellation occurs, and the net result is spin 1/2 for the neutron as a whole. Now, each of these quarks is generating its own magnetic moment. The up quark, with charge plus 2/3, generates a magnetic moment that points along its spin direction. The down quarks, each with charge minus 1/3, generate magnetic moments that point opposite to their spin directions. This reversal happens because the down quark's charge is negative. For a negatively charged particle, the magnetic moment points opposite to the spin. This is the same reason that the electron's magnetic moment points opposite to the electron's spin. Negative charge reverses the relationship between spin direction and magnetic direction. So, inside the neutron, you have 3 little magnets. Each one has a specific strength determined by its charge and mass. Each one points in a direction determined by its spin orientation and the sign of its charge. The neutron's total magnetic moment is the sum of all 3, and when you do the calculation, accounting for the specific quark charges, the specific spin arrangement mandated by quantum mechanics, and the way positive and negative charges reverse the relationship between spin and magnetic moment, you get a striking result. The contributions do not cancel. The down quarks win. Here is why. The neutron has 2 down quarks and 1 up quark. Each down quark has charge minus 1/3, and each generates a magnetic moment in a specific direction relative to the neutron's overall spin. The single up quark has charge plus 2/3 and generates its own contribution. When you add up all 3 contributions, accounting for the spin arrangement and the charge signs, the net magnetic moment points opposite to the neutron's spin direction. This is why the neutron's magnetic moment is negative. The word negative here means the magnetic moment vector is anti-parallel to the spin vector. It points the other way. For comparison, consider the proton. The proton has 2 up quarks and 1 down quark. The same calculation gives a net magnetic moment that points along the spin direction. The up quarks dominate, and their positive charges align the magnetic moment with the spin. The proton's magnetic moment is positive. Its magnetism points in the same direction as its spin. This comparison reveals something elegant. The proton and the neutron are mirror images of each other in quark content. The proton is up-up-down. The neutron is up-down-down. Swap the roles of up and down quarks, and you swap the proton for the neutron. Their magnetic moments are related by this same swap. The proton's moment is positive and roughly 2.8 nuclear magnetons. The neutron's moment is negative and roughly minus 1.91 nuclear magnetons. The ratio of these two values, about -2/3, is exactly what the simplest version of the quark model predicts. Two particles, same fundamental mechanism, different quark compositions, and therefore different magnetic moments. The same recipe, different ingredients, different results. But both entirely explained by quarks with fractional charges and quantum spin. This was a spectacular success for the quark model. When physicists first calculated the neutron's magnetic moment from the quark picture, they got a result that was remarkably close to the experimentally measured value. Not perfect, not exact to 10 decimal places, but strikingly close. Close enough that nobody could dismiss it as coincidence. The quark model was producing quantitative predictions about one of the most puzzling measurements in nuclear physics, and those predictions were working. The neutron's impossible magnetism was no longer impossible. It was inevitable once you accepted that the neutron was made of charged quarks with quantum spin. But the story does not end here. Because when physicists tried to push deeper, to extract more precise predictions, they discovered something disturbing. The simple quark model, for all its successes, was not telling the whole story. In the simple picture, the neutron's spin comes entirely from the spins of its three quarks. Two quark spins partially cancel, one remains, and the result is the neutron's total spin of 1/2. The quarks carry all the angular momentum. There is nothing else contributing. But in the late 1980s, a series of experiments at CERN and SLAC shattered this comfortable picture. The experiments used beams of polarized particles, meaning particles whose spins were all aligned in a known direction, and scattered them off polarized nucleon targets. By carefully measuring how the scattered particles emerged, physicists could determine how much of the nucleon's total spin was carried by the quark's spins alone. The result was stunning and became known as the proton spin crisis, though it applied equally to the neutron. The quark's spins accounted for only a small fraction of the total spin. Early measurements suggested the quarks might carry as little as about 12% of the total spin. Later, more refined experiments revised the number upward. But even the best modern measurements indicate that quark spins contribute roughly 25 to 30% of the nucleon spin. Not half, not most, roughly a quarter to a third. The remaining 70 to 75% must come from somewhere else. To appreciate just how shocking this result was, you need to understand what physicists expected going in. The quark model had been spectacularly successful. It explained the particle zoo. It predicted the neutron's magnetic moment to good approximation. It correctly described the ratio between the proton and neutron magnetic moments. Everything about the simple three-quark picture was working beautifully. And in that picture, the neutron's spin came entirely from the three quark spins combining in a specific quantum arrangement. There was no room for anything else. No need for anything else. The model was clean, elegant, and it worked. So, when experimentalists at CERN used muon beams to probe the spin structure of nucleons and found that the quark spins contributed only a fraction of the total, it was as if someone had pulled the foundation out from under a building that everyone thought was standing perfectly solidly. The experiment, performed by the European Muon Collaboration and often referred to by physicists as the EMC experiment, measured something called the spin structure function of the proton. This is a mathematical object that encodes how the proton's spin is distributed among its internal constituents. The measurement involved scattering polarized muons, heavy cousins of the electron, with their spins aligned in a known direction off polarized proton targets. By measuring the difference in scattering rates when the muon spin was parallel versus antiparallel to the proton spin, the experiment could isolate the contribution of quark spins to the proton's total angular momentum. The expectation was clear. Quark spins should account for most of the proton's spin, somewhere around 60% or more in the simplest quark model estimates. When the results came in, the number was consistent with 0. The quark's spins appeared to contribute essentially nothing to the total spin. This was so startling that it was initially met with disbelief. Physicists checked the data, reanalyzed the systematics, and debated the interpretation. Subsequent experiments at SLAC, CERN, and other facilities refined the measurement. The number crept up from 0 to something closer to 25 or 30%, but it never approached the 60% or more that the simple quark model demanded. The crisis was real. The name spin crisis was not an exaggeration. It genuinely threatened the coherence of the quark model, the most successful organizational framework in particle physics. If quarks did not carry the spin of the nucleon, what did? The answer had to come from somewhere inside the neutron, because the total spin was measured and known to be 1/2. Angular momentum is conserved. It cannot appear from nowhere or vanish without trace. If the quark spins only provided a quarter of the total, the remaining 3/4 had to be hiding in other degrees of freedom within the same system. The resolution, as we now understand it, involves recognizing that the simple quark model was never the full story. It was a first approximation, a sketch that captured the broad outlines while missing crucial details. The neutron is not 3 quarks sitting passively with their spins aligned in a tidy quantum state. It is a violently dynamic system where quarks are in constant motion, gluons are constantly being exchanged, and the quantum vacuum inside the neutron is alive with virtual quark-antiquark pairs. All of these contribute angular momentum. The simple model ignored most of this activity. The spin crisis forced physicists to take the full complexity of the neutron's interior seriously, and in doing so, it deepened our understanding enormously. Today, mapping the complete spin budget of the nucleon remains one of the most active areas of research in nuclear and particle physics. The electron-ion collider, currently under construction at Brookhaven National Laboratory, is designed in large part to answer exactly this question with unprecedented precision. It will collide polarized electrons with polarized protons and heavier nuclei, allowing physicists to measure quark and gluon contributions to the nucleon's spin with far greater accuracy than any previous experiment. When it begins operating, it will represent the next major chapter in a story that began with the EMC experiment's startling discovery nearly 4 decades ago. These additional contributions deserve a closer look, because each one reveals something important about the neutron's interior that the simple quark model completely overlooked. The first source is the orbital angular momentum of the quarks. In the simple quark model, the quarks are imagined to be in a ground state with no orbital motion. They just sit there with their spins, like 3 compass needles embedded in a ball of putty. But in reality, the quarks are not stationary. They are confined to a tiny volume roughly 1 femtometer across, and the uncertainty principle guarantees they have significant momentum. They are buzzing around constantly. This internal motion carries orbital angular momentum, the same kind of angular momentum that Earth carries as it orbits the Sun, or that an electron carries as it moves around an atomic nucleus in certain quantum states. In the simple model, this orbital angular momentum was assumed to be 0. But the experiments proved that assumption wrong. The quarks are moving inside the neutron, and their motion contributes meaningfully to the total angular momentum. The second source is even more surprising. The gluons themselves carry angular momentum. Gluons are spin-1 particles. They are the force carriers of the strong force, constantly being emitted and absorbed by quarks, flickering in and out of existence throughout the neutron's interior. Each gluon carries 1 unit of spin angular momentum, and collectively, the gluon field inside the neutron can carry a significant fraction of the total spin. This was unexpected, because in the simple quark model, gluons were treated as passive binding agents. They held the quarks together, but were not considered important contributors to the neutron's spin. The experiments showed otherwise. The gluon field is not just a background scaffold. It is an active, dynamic participant in the neutron's quantum properties. So the modern understanding of the neutron's spin, and therefore its magnetic moment, involves three contributions: quark spin, quark orbital angular momentum, and gluon angular momentum. All three combine to produce the neutron's total spin of 1/2, and all three influence its magnetic moment. This makes precise calculation of the neutron's magnetic moment extraordinarily difficult, because you need to account for all the quantum fluctuations of quarks and gluons inside a strongly interacting system. The simple quark model gives you a good first approximation, getting the sign right and the magnitude approximately right. But the full answer requires the complete machinery of quantum chromodynamics, the theory of the strong force, applied to a three-body bound state with gluon fields and virtual quark-antiquark pairs and orbital motion all tangled together. This is one of the grand challenges of modern theoretical physics. Lattice quantum chromodynamics, a computational approach that places the equations of the strong force on a discrete grid and solves them numerically using powerful supercomputers, has made significant progress. In recent years, lattice calculations have reproduced the neutron's magnetic moment to within a few % of the measured value, starting from nothing but the fundamental equations of the strong force and the known quark masses. This is a remarkable achievement. You write down the basic laws governing quarks and gluons, feed them into a supercomputer, let the machine grind through billions of calculations, and out comes a number that matches what experimentalists measure in the laboratory. Theory and experiment agree. The mechanism works. The neutron's magnetism genuinely arises from the quantum spin and motion of its internal quarks and gluons, just as the quark model predicted, but with additional layers of complexity that the simple model could not capture. And this brings us to a deeper appreciation of what the neutron actually is as a physical object. It is not a machine. It is not a classical device with gears and moving parts. It is a bound quantum state of quarks and gluons, described not by definite positions and trajectories, but by a quantum wave function that encodes the probabilities of finding each quark and gluon in any particular configuration. The quarks are not little balls sitting at fixed locations. They are quantum fields smeared across the neutron's volume, constantly fluctuating. The gluons are quantum fields too, ceaselessly being exchanged, split, and recombined. Virtual quark-antiquark pairs bubble up from the vacuum inside the neutron and disappear again on timescales so short they are barely conceivable. In this environment, asking where exactly is the up quark right now is not a meaningful question. The quark does not have a definite position. It has a probability distribution. The best you can say is that there is a certain probability of finding it at any given point inside the neutron. Similarly, asking how fast is the down quark moving does not have a crisp answer. The quark exists in a superposition of many momentum states simultaneously. The neutron's magnetic moment emerges from this entire quantum ensemble. It is not the result of one quark doing one thing. It is the collective outcome of all three quarks, all the gluons, and all the virtual particles contributing simultaneously through their spins, their orbital motions, and their mutual interactions. The magnetic moment is a property of the whole system, not of any individual part. This is what makes the neutron's magnetism genuinely profound as a physics result. It demonstrates that composite quantum systems can possess properties that their individual parts, considered in isolation, would not fully explain. You cannot simply add up three isolated quark magnetic moments and get the neutron's magnetic moment. You must account for how those quarks are bound together, how they interact, how the gluon field modifies their behavior, and how the quantum state of the entire system determines the final result. The binding matters. The interactions matter. The quantum correlations matter. The whole is not simply the sum of its parts. It is something richer. Consider an analogy. A single musician can play notes. Three musicians playing separately produce three independent melodies. But three musicians playing together as an ensemble produce something qualitatively different. harmonies emerge, rhythms interlock. The music of the group is not just the sum of 3 solo performances. The interaction between the musicians, the way they listen to each other and respond, creates something new. The neutron is like that ensemble. Its magnetic moment is the harmony that emerges from the interaction of 3 quarks bound together by the strong force. Each quark contributes, but the final result depends on how they interact within the bound state. And the fact that this harmony produces a non-zero magnetic moment for a particle with 0 total charge is what makes the neutron so remarkable. The charges cancel. The magnetism does not. The cancellation and the survival are both governed by the same quantum mechanics, the same quark model, the same underlying physics. They are not contradictions. They are different consequences of the same internal structure, each following its own mathematical rules. Charge depends on the sum of quark charges, which is 0. Magnetism depends on the sum of quark magnetic moments, weighted by their spin orientations and influenced by orbital and gluon contributions, which is not 0. 2 different properties, 2 different rules for combining, 2 different outcomes. Both perfectly consistent. Both inevitable once you know what the neutron is made of and how its parts behave. The neutron's magnetic moment of approximately minus 1.91 nuclear magnetons is not some minor curiosity. It is a precision test of our understanding of the strong force. It is a quantitative prediction that quantum chromodynamics must reproduce, and does reproduce, when calculated with sufficient computational power. It is a direct window into the internal structure of matter, a measurable number that encodes information about quark charges, quark spins, quark orbital motion, gluon dynamics, and the quantum binding that holds everything together. Every digit of that number tells a story about the violent, beautiful, impossibly complex quantum world that exists inside every neutron in the universe. We have spent this journey tracing the neutron's magnetism from its paradoxical discovery to its quantum mechanical explanation. A particle with 0 total charge that behaves like a magnet because its interior is alive with charged quarks carrying quantum spin and orbital angular momentum, bound together by a furious storm of gluons. The mechanism is beautiful, but physics does not exist in a vacuum. The real measure of any discovery is what it allows you to do, what it teaches you about the universe, and what doors it opens that would otherwise remain closed. The neutron's magnetic moment is not just a curiosity of subatomic structure. It is a tool, one of the most powerful and versatile tools in all of modern science. And it has changed our understanding of everything from the arrangement of atoms in crystals to the most extreme environments in the cosmos. Let's start with something practical, something that affects technology, medicine, and materials science every single day: neutron scattering. When physicists want to understand how atoms are arranged inside a material, they need a probe small enough to interact with individual atoms and sensitive enough to reveal their positions. X-rays have been used for this purpose since Max von Laue and the Bragg family pioneered X-ray crystallography in the early 1900s. You shine a beam of X-rays at a crystal. The X-rays bounce off the atoms inside, and the pattern of scattered X-rays tells you where the atoms are. This technique revolutionized chemistry, biology, and materials science. The structure of DNA was determined using X-ray crystallography. The arrangement of atoms in metals, ceramics, semiconductors, and proteins has been mapped with X-rays. It is one of the most important experimental techniques in the history of science. But X-rays have limitations. X-rays interact primarily with electrons. The more electrons an atom has, the more strongly it scatters X-rays. This means heavy atoms like iron, copper, and lead scatter X-rays powerfully, while light atoms like hydrogen, lithium, and carbon scatter them weakly. If you want to find hydrogen atoms in a crystal structure, X-rays are nearly blind. They simply cannot see hydrogen well because hydrogen has only one electron. This is a serious problem because hydrogen is everywhere. It is in water, in biological molecules, in many technologically important materials. Understanding where hydrogen atoms sit inside these structures is often critical, and X-rays struggle to tell you. Neutrons solve this problem in a fundamentally different way. Unlike X-rays, which interact with the electron cloud around atoms, neutrons interact with the atomic nucleus itself through the strong nuclear force. And crucially, the strength of this interaction does not scale smoothly with atomic weight. Some light nuclei scatter neutrons very strongly. Hydrogen is one of them. Neutron scattering can see hydrogen atoms clearly, even when they are surrounded by much heavier atoms that would completely overshadow them in an X-ray experiment. This capability alone makes neutron scattering indispensable in chemistry and biology. When researchers want to determine the exact positions of hydrogen atoms in a protein, a pharmaceutical compound, or a fuel cell membrane, they turn to neutron scattering because no other technique can do the job as well. But here is where the neutron's magnetic moment becomes essential. Because neutrons are tiny magnets, they interact not only with atomic nuclei through the strong force, but also with the magnetic fields produced by unpaired electrons in magnetic materials. When a neutron beam passes through a magnetic material, the neutron's magnetic moments interact with the material's internal magnetic structure. The way the neutrons scatter depends on how the magnetic moments of the atoms inside the material are arranged. By analyzing the scattering pattern, physicists can construct detailed maps of the magnetic order inside the material, atom by atom. This is called magnetic neutron scattering, and it is something X-rays simply cannot do. X-rays interact with charge, not with magnetic moments. They cannot directly reveal how the tiny atomic magnets inside a material are oriented. Neutrons can, precisely because they themselves are magnets. The neutron's magnetic moment acts as a sensor, a probe that feels the magnetic fields inside the target and reports back through the scattering pattern. Without the neutron's magnetism, this entire technique would not exist. Magnetic neutron scattering has been transformative. It revealed the magnetic structures of antiferromagnets, materials where neighboring atomic magnets point in alternating opposite directions, cancelling the bulk magnetism but creating a hidden magnetic order at the atomic scale. It helped physicists understand ferrites, the magnetic ceramics used in electronics. It played a central role in unraveling the physics of high-temperature superconductors, materials that conduct electricity with zero resistance at temperatures far above what was previously thought possible. The magnetic interactions in these materials are intimately connected to their superconducting behavior, and neutron scattering was the tool that mapped those interactions. Clifford Shull and Bertram Brockhaus shared the Nobel Prize in Physics in 1994 for their pioneering work in neutron scattering techniques. Shull developed methods for using neutron diffraction to determine the structure of materials, including their magnetic structure. Brockhaus developed inelastic neutron scattering, which probes the dynamics of atoms, how they vibrate, how their magnetic excitations propagate through a crystal. Both techniques rely fundamentally on the fact that the neutron has a magnetic moment. If the neutron were magnetically blank, if its magnetic moment truly were zero, as Dirac's equation predicted for a structureless neutral particle, none of this would work. An entire branch of experimental physics would simply not exist. Today, large neutron scattering facilities operate around the world. These facilities use nuclear reactors or powerful particle accelerators to generate intense beams of neutrons, which are then directed at samples under study. Researchers use these facilities to investigate everything from the molecular structure of new drugs to the behavior of quantum magnets to the properties of materials under extreme pressure and temperature. Thousands of scientific papers every year rely on data obtained through neutron scattering, and every single one of those experiments depends on the neutron's magnetic moment, the very property that once seemed impossible for a neutral particle to possess. Now let's move from the laboratory to the nucleus. The neutron's magnetic moment plays a significant role in nuclear physics, shaping the behavior of atomic nuclei in ways that directly affect the stability and properties of matter. Inside a nucleus, protons and neutrons are packed together at extraordinary densities. The nuclear force binds them tightly, but within that bound state, their individual properties still matter. Both protons and neutrons carry magnetic moments, and these moments interact with each other through magnetic dipole forces. These magnetic interactions are much weaker than the nuclear force that holds the nucleus together, but they are not negligible. They contribute to the detailed energy levels of nuclei, to the way nuclei absorb and emit radiation, and to the precise arrangement of nucleons within the nuclear interior. Nuclear magnetic resonance, the phenomenon underlying MRI machines in hospitals, depends on the magnetic moments of nuclei. When you place a nucleus in a strong magnetic field, its magnetic moment interacts with the field, and the nucleus precesses, wobbling like a top at a specific frequency that depends on the strength of the magnetic moment and the strength of the applied field. By detecting this precession frequency, you can identify which nuclei are present and learn about their chemical environment. In medical MRI, the nuclei being detected are primarily hydrogen nuclei, which are just single protons. But in research applications, nuclear magnetic resonance techniques are applied to many different nuclei, and the neutron's magnetic moment contributes to the magnetic properties of every nucleus that contains neutrons. Consider an isotope of helium called helium-3. Its nucleus contains 2 protons and 1 neutron. The magnetic moment of this nucleus depends on the magnetic moments of all 3 nucleons and how their spins are arranged inside the nucleus. The neutron's contribution is essential to getting the right answer. Change the neutron's magnetic moment, and you change the nuclear magnetic moment of helium-3, which changes how it behaves in magnetic resonance experiments. The same is true for virtually every nucleus heavier than hydrogen. The neutron's magnetism is woven into the magnetic identity of all nuclear matter. Now let's go much farther. Let's leave the laboratory and the atomic nucleus behind and travel to one of the most extreme environments in the known universe, the neutron star. When a massive star reaches the end of its life, it can collapse in a catastrophic supernova explosion. If the remnant core is between roughly 1.4 and about 2.1 times the mass of our Sun, the gravitational compression is so intense that protons and electrons are squeezed together, converting into neutrons through a process governed by the weak nuclear force. The result is a neutron star, an object containing roughly the mass of the Sun compressed into a sphere with a radius of roughly 10 to 12 kilometers. A teaspoon of neutron star material would weigh approximately 4 billion tons on Earth. The density is almost incomprehensible. It exceeds the density of an atomic nucleus, which is already 100 trillion times denser than water. And neutron stars are magnetic. Enormously, spectacularly, overwhelmingly magnetic. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's own magnetic field, and many thousands to millions of times stronger than the most powerful magnets ever built in a laboratory. Some neutron stars, called magnetars, have fields reaching 1 quadrillion times the strength of Earth's magnetic field. These are the most powerful magnetic fields known to exist anywhere in the observable universe. Where does this magnetism come from? The answer traces directly back to the neutron's magnetic moment. A neutron star is made primarily of neutrons, and every one of those neutrons is a tiny magnet. When trillions upon trillions of neutrons are packed together at nuclear density, their individual magnetic moments can align and reinforce each other, creating a macroscopic magnetic field of staggering intensity. The process is not simple. It involves complex interactions between the neutrons, the remaining protons and electrons, superfluid dynamics, and the extreme physics of matter at nuclear density. But at its foundation, the neutron star's magnetism begins with the same quantum mechanical property we have been exploring throughout this journey. The magnetic moment of a single neutron arising from the spins and motions of its internal quarks. Magnetars, the most extreme examples, have magnetic fields so powerful that they distort the shapes of atoms, making them elongated rather than spherical. At the surface of a magnetar, the magnetic field is strong enough to affect the vacuum itself, producing exotic quantum electrodynamic effects. Light passing through such a field splits into two differently polarized components that travel at slightly different speeds, a phenomenon called vacuum birefringence that was predicted by quantum electrodynamics decades ago and has only recently been observed in astrophysical data from neutron stars. The neutron's modest magnetic moment, negative 1.91 nuclear magnetons, seems tiny on its own, but multiplied across the roughly 10 to the 57th power neutrons in a neutron star and amplified by the extreme conditions of gravitational collapse, it produces some of the most dramatic electromagnetic phenomena in the cosmos. It is worth pausing here to think carefully about how this scaling works, because the leap from one neutron's magnetic moment to a magnetar's field is one of the most dramatic amplifications in all of physics. A single neutron's magnetic moment is roughly minus 1.91 nuclear magnetons. In standard units, that translates to approximately minus 9.66 times 10 to the minus 27 joules per Tesla. That is an almost unimaginably tiny number. If you held a single neutron in your hand, which you cannot because it would decay in minutes, its magnetic field would be completely undetectable by any instrument you could build. It would be lost in the thermal noise of the surrounding air molecules. It would be drowned out by the magnetic fields produced by the iron in your blood or the electrical currents in your nerves. A single neutron's magnetism is, for all practical purposes, invisible. But a neutron star contains approximately 10 to the 57th power neutrons. That is a 1 followed by 57 zeros. And these neutrons are not spread out over a comfortable volume like atoms in a gas. They are compressed to nuclear density, roughly 230 million tons per cubic centimeter. At such densities, the neutrons are packed so tightly that they are practically touching, their wave functions overlapping, their magnetic moments separated by distances measured in femtometers. When you have that many tiny magnets packed that closely together, even partial alignment of their moments produces a collective magnetic field of staggering strength. The amplification is not purely a matter of addition. In a normal material, thermal energy constantly randomizes the orientations of atomic magnetic moments, preventing full alignment. This is why you cannot magnetize a piece of iron by cooling it to room temperature and hoping for the best. You need an external field or a special crystal structure to force alignment. But in a neutron star, the conditions are entirely different. The gravitational collapse that creates the star also compresses and freezes magnetic flux from the original star into the tiny volume of the remnant. The magnetic field of the parent star, which might have been modest by stellar standards, is amplified by the conservation of magnetic flux as the iron core collapses from a radius of a few thousand kilometers to a neutron star only about 12 kilometers in radius. This compression alone can amplify the field by a factor of roughly 100,000, and additional dynamo effects during the violent first seconds of the neutron star's life can amplify it by many more orders of magnitude. And then, on top of this compressed fossil field, the individual neutron magnetic moments contribute their own additional magnetism through quantum mechanical interactions between the densely packed neutrons. The result is a magnetic field so intense that it defies ordinary comparison. The strongest continuous magnetic field ever produced in a laboratory on Earth is roughly 45 Tesla. A magnetar's field can exceed 10 to the 11th Tesla. That is more than 1 billion times stronger than the best laboratory magnet. At these field strengths, atoms are distorted into long, thin cylinders aligned with the field. The energy stored in the magnetic field near a magnetar's surface exceeds the energy output of our Sun over thousands of years, compressed into a region smaller than a city. Occasional rearrangements of this field, called starquakes, release bursts of gamma radiation so intense that one event from a magnetar, roughly 50,000 light-years away, was powerful enough to measurably compress Earth's magnetosphere in December of 2004. A quantum property of a single neutron, amplified by gravitational collapse and sheer numbers, producing explosions detectable across the galaxy. The connection between the microscopic and the cosmic could hardly be more dramatic. Pulsars, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles, are another consequence. As the neutron star rotates, its magnetic field sweeps through space like a cosmic lighthouse. If Earth happens to lie in the path of the beam, we detect a pulse of radiation with each rotation. Some pulsars spin hundreds of times per second, producing pulses with extraordinary regularity. Pulsars are among the most precise natural clocks in the universe, and their behavior is governed by the interplay between their rapid rotation and their intense magnetic fields that ultimately trace their origin to the magnetic moments of the neutrons packed inside. Now let's turn to what might be the most profound application of the neutron's magnetic moment: precision tests of fundamental physics. The neutron's magnetic moment has been measured to extraordinary accuracy. We know its value to better than 8 significant figures. But physicists are not satisfied with measuring the magnetic moment alone. They are also searching for something that, as far as we know, does not exist: the neutron electric dipole moment. An electric dipole moment would mean that the neutron's internal charge distribution is slightly asymmetric in a very specific way. Not just the positive core and negative outer shell we discussed earlier, which is symmetric around the neutron's center, but a separation of positive and negative charge along the neutron's spin axis. If the neutron had an electric dipole moment, it would mean that the top of the neutron, defined by the direction of its spin, is slightly more positive than the bottom, or vice versa. The neutron would be not just a tiny magnet, but also a tiny electric antenna, with one end slightly positive and the other slightly negative. Why does this matter? Because an electric dipole moment of the neutron would violate a fundamental symmetry of physics called time reversal invariance. In everyday language, time reversal invariance means that the laws of physics look the same whether time runs forward or backward. If you filmed a simple physical process, like 2 billiard balls colliding, and played the film backward, the reversed version would also obey the laws of physics. You could not tell which version was the real one. Time reversal invariance, often called T-symmetry, is closely related to another symmetry called CP symmetry through a deep theorem of quantum field theory called the CPT theorem. This theorem states that every valid physical theory must be symmetric under the combined operation of charge conjugation, parity inversion, and time reversal. If CP symmetry is violated, T symmetry must also be violated to keep CPT intact. We know CP violation exists. It has been observed experimentally in the decays of certain particles called kaons and B mesons. So T violation must exist too. And one way T violation could show up is through a non-zero electric dipole moment of the neutron. Here is where things get exciting. The standard model of particle physics predicts that the neutron should have an electric dipole moment, but an incredibly tiny one. So tiny that it is far below the sensitivity of any current experiment. If experiments were to detect a neutron electric dipole moment at levels accessible to current technology, it would mean that the standard model is incomplete. It would be direct evidence of new physics beyond our current understanding, potentially connected to supersymmetry, extra dimensions, or other exotic theoretical frameworks. It could even help explain one of the deepest mysteries in cosmology. Why does the universe contain matter at all? The universe began, as far as we understand, with equal amounts of matter and antimatter. But today, everything we see, every star, every planet, every atom in your body, is made of matter. The antimatter is gone. Something must have caused an imbalance, a slight preference for matter over antimatter in the early universe. The known sources of CP violation in the standard model are far too small to explain this imbalance. There must be additional, undiscovered sources of CP violation. And a neutron electric dipole moment larger than the standard model predicts would be evidence of exactly such a source. It could help explain the most basic question of existence. Why is there something rather than nothing? This question, why there is something rather than nothing, might sound philosophical, and it is. But it is also a precise, quantifiable physics problem. We can calculate exactly how much CP violation the standard model produces through known mechanisms, primarily through the complex phase in the quark mixing matrix. And the answer falls short by many orders of magnitude. The known CP violation is far too small to explain the observed ratio of matter to antimatter in the universe. Something else must be contributing, some additional source of asymmetry that we have not yet discovered. The neutron electric dipole moment is one of the most sensitive probes of this unknown source. Different theories beyond the standard model, theories involving supersymmetric particles, theories with additional Higgs bosons, theories with extra spatial dimensions, all predict different values for the neutron's electric dipole moment. Some predict values just below current experimental sensitivity. Others predict values that current experiments have already ruled out, eliminating those theories from consideration. Every time experimentalists push the sensitivity downward by another factor of 10, they sweep away entire families of theoretical proposals and tighten the constraints on what the true theory of nature can look like. This makes the neutron electric dipole moment search one of the highest stakes experiments in fundamental physics. It is a rare case where a single measurement, a single number, could simultaneously confirm new physics beyond the standard model, identify the mechanism responsible for the matter-antimatter asymmetry, and point the way toward a deeper theory of nature. All from measuring the electromagnetic properties of a particle that was once assumed to have no electromagnetic properties at all. Experiments searching for the neutron electric dipole moment, often called neutron EDM experiments, are among the most precise measurements in all of physics. They work by trapping ultra-cold neutrons that have been slowed to speeds of just a few meters per second, in specially designed chambers. The neutrons are exposed to parallel and antiparallel electric and magnetic fields, and physicists measure whether the neutron's precession frequency changes when the electric field is reversed. If the neutron has an electric dipole moment, its energy will shift slightly depending on the direction of the electric field relative to its spin. And this shift will produce a measurable change in precession frequency. Norman Ramsey, who developed the technique of separated oscillatory fields used in these measurements, received the Nobel Prize in Physics in 1989, partly for this work. So far, no neutron electric dipole moment has been detected. The current upper limit is extraordinarily small, roughly 26 orders of magnitude smaller than the neutron's magnetic moment. This null result is itself enormously informative. It rules out many theoretical models that predict larger values. It constrains the parameters of speculative theories, and it continues to push experimental precision deeper and deeper, narrowing the space where new physics can hide. The fact that this entire experimental program exists, that thousands of physicists and engineers around the world devote their careers to measuring properties of the neutron with exquisite precision, is a direct consequence of the neutron's internal structure. A truly fundamental, structureless, neutral particle would have exactly zero magnetic moment and exactly zero electric dipole moment. There would be nothing to measure, nothing to search for, no precision tests to run. But because the neutron is a composite object with a rich internal landscape of charged quarks and dynamic gluon fields, its electromagnetic properties encode information about the deepest laws of physics. Every improvement in measurement precision is a deeper look into the quantum interior of the neutron, and through that interior, into the fundamental symmetries and forces that govern the universe. And this brings us back to the central lesson of this entire story. The neutron's magnetism is not just a surprising fact about one particular particle. It is a case study in one of the most important principles in all of science. Surface simplicity almost always hides internal complexity. The neutron appears simple. It is neutral. It has no electric charge. From the outside, it looks like a blank, featureless object with nothing electromagnetic to offer the universe. Zero. Nothing there. Move along. And for decades, that surface impression satisfied most physicists. The neutron was the quiet partner in the nucleus, contributing mass and nuclear binding, but electromagnetically silent. Then measurements revealed its magnetic moment, and that single number blew the simple picture apart. A number that should have been 0 turned out to be nearly 2 nuclear magnetons, and suddenly the neutron had an interior. It had parts. It had structure. It had a whole hidden world of charged quarks and gluon fields and quantum spin and orbital angular momentum and virtual particle pairs bubbling in and out of existence. This pattern repeats throughout the history of physics. Things that look simple on the surface turn out to be complex underneath. The atom looked like an indivisible sphere until Rutherford found the nucleus. The nucleus looked like a bag of protons and neutrons until deep inelastic scattering found quarks. The vacuum looked like empty nothing until quantum field theory revealed it is seething with virtual particles and fluctuating fields. At every level, peeling back the surface reveals hidden structure, and each layer of structure brings new phenomena, new properties, new capabilities that the simpler picture could not explain. The neutron's magnetism is a perfect example of this principle in action. Zero total charge does not mean zero electromagnetic identity. The charges cancel, but the charged parts remain. Their spins and motions create magnetism that survives the cancellation. The whole is richer than the sum of its parts. Neutrality is not emptiness, it is balance. And balance, in quantum mechanics, is a far more interesting and subtle state than absence. Every neutron in the universe carries this hidden richness. Every neutron in every nucleus of every atom in your body is a tiny magnet, its magnetism arising from the same quark dynamics we have explored tonight. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it contains neutrons. And every one of those neutrons is a seething quantum system of charged quarks and gluon fields, carrying a precise magnetic moment that encodes information about the deepest forces in nature. You are, in a very real sense, built from these hidden magnetic worlds. Trillions upon trillions of them, each one a testament to the fact that nothing in nature is as simple as it first appears. And perhaps that is the most enduring gift of this story. Not just the specific answer about quarks and gluons and quantum spin, but the broader lesson about how we should approach the world. The neutron taught physicists to be suspicious of surfaces, to distrust labels like neutral or empty or nothing, to always ask what lies beneath, even when the surface looks perfectly smooth and featureless and boring. That instinct, the refusal to accept that something is truly as simple as it appears, has driven some of the greatest discoveries in the history of science. When you look at the night sky, the space between the stars looks empty, but it is not. It is filled with cosmic microwave background radiation, with neutrinos streaming in every direction, with dark matter whose nature we still do not understand. Emptiness is almost always an illusion in physics. When you look at an atom, it appears to be mostly empty space between the nucleus and the electrons. But that space is filled with electromagnetic fields, with virtual photons being exchanged, with quantum fluctuations that give rise to measurable forces. The vacuum of empty space itself, the most nothing thing you can imagine, turns out to be seething with virtual particle-antiparticle pairs popping into and out of existence, producing measurable effects like the Casimir force and the Lamb shift. Everywhere physicists have looked and found apparent simplicity or emptiness, they have eventually discovered hidden complexity. The neutron is one of the most beautiful examples of this pattern. A particle labelled neutral, assumed to be electromagnetically inert, turned out to contain a rich interior of fractionally charged quarks, dynamic gluon fields, quantum spin, orbital angular momentum, and virtual particle pairs. Its magnetic moment, the quantity that should have been zero, turned out to encode some of the deepest information about the structure of matter and the symmetries of the universe. And the search for its electric dipole moment, a quantity that might also be zero, or might be the key to understanding why matter exists at all, continues to push the boundaries of experimental precision and theoretical understanding. If there is one thing the neutron teaches us, it is that zero is the most interesting number in physics. Not because zero means nothing, but because in the quantum world, zero almost never means nothing. Zero means balance. Zero means cancellation. Zero means that something fascinating is hiding just beneath the surface, waiting for someone curious enough and clever enough to look. The neutron asked us a question that seemed impossible. How can something with no charge be a magnet? And the answer turned out to be one of the most illuminating truths in all of physics. Because zero does not mean empty. Because neutral does not mean featureless. Because the universe is always more complicated, more beautiful, and more deeply structured than it looks from the outside. The next time someone tells you that something is nothing, remember the neutron. Look closer. There is almost certainly something remarkable hiding inside.